Chapter 5, Section 2, Ionic Bonding and Salts. In this section of Chapter 5, we are going to look at ionic compounds and the properties ionic compounds have. And some of this, of course, may sound familiar from when we were in Chapter 5, Section 1, and we looked at the types of chemical bonds. So ionic compounds are held together by ionic bonds. And what you should remember about an ionic bond is that there is a transfer of electrons from a metal to a nonmetal. And within that ionic bond, there is a small whole number ratio of cations to anions. And you should recall that cations are the positively charged ions, and anions are the negatively charged ions. And they are pulled together because they're oppositely charged, so they're electrically attracted to each other. And unlike covalent compounds that form molecules, ionic compounds form a crystalline structure. Now, the ions, when they're pulled together, you have a ratio of positive charge and a ratio of negative charge that are equal to each other. So the crystal lattice itself is electrically neutral. So for example, if you think back to the video you would have watched in Chapter 5, Section 1, we saw sodium metal interacting with chlorine gas. And at this point, we should know that sodium is a group 1 element, so it has one electron to give away. And chlorine is a group 17 element, and it wants to attract another electron. This way they both have an octet. So in this case, the whole number ratio would be 1 sodium ion for every chloride ion. So ionic compounds are made up of ions. And again, they're made up of cations, which are the positively charged ions, and anions, which are the negatively charged ions. And those ions interact because they are electrically attracted to each other. And because of this electrical attraction, it makes it, if you think back to where we talked about types of bonds, ionic bonds are the strongest. And again, in chemistry, lots of times we make observations on the macroscopic level, and this helps us learn about what's going on the subatomic level. So for example, when we looked at the types of chemical bonds lab, we saw that these were not able to be melt with a candle, so this tells us they have high melting and boiling points. The other thing to note about ionic compounds is that these are typically solids at room temperature, whereas covalent compounds are typically either liquids or gases at room temperature because they have weaker bonds. So because compounds have this crystal lattice, they're in a very fixed position, so it takes lots of energy to move ions out of their fixed position. So if we look at this table from your textbook, we can see, if we look at the top half of the table, it reinforces our discussion that ionic compounds, and one of the ways that I can recognize that these are all ionic compounds is that it's a metal followed by a nonmetal in the compound, have very high melting and boiling points. And if I look at the bottom part of the table, these are all covalent compounds. They're sharing electrons, and they have very low melting and boiling points. So again, this tells us they have weak bonds. And again, we should be able to recognize that covalent compounds are made up of 2 nonmetals. Okay, other properties of ionic compounds. So when we did the types of chemical bonds lab, we dissolved potassium iodide, for example, in water, and then we tested conductivity, and we saw that it conducts. However, it's only able to conduct when the solid has been dissolved in water, or it's been melted, so it's in a liquid state. And then just to reinforce, in order for something to conduct, it has to have a charged particle that can move. In the case of ionic compounds, they have ions. Covalent compounds do not have ions, so this is why they're non-conductive. So why does it have to be dissolved? Why does it have to melt? The reason why is because, again, in the solid structure, you have a crystal lattice where ions are in a fixed position. We need those particles to be able to move, and they can do that if they're dissolved or they're in a liquid state of matter. Ionic compounds are hard, so they can resist a large force being applied to it. And part of the reason why they can resist that force is because they have a pattern of cations to anions. However, in some cases, we get a force that causes a shift in layers. And when layers shift, then you can see from the diagram that we get like charges near each other, and we should know that like charges repel, and it breaks apart our lattice, so they're brittle. Okay, so here's sodium chloride, which is an ionic compound. It's made up of a metal and a nonmetal. You can see in the solid form, you have your tightly packed crystal lattice where the ions are in a very fixed position. In figure B, you're melting them, so notice that there's some space, so it allows the particles to move. And also when dissolved, again, you have movement of those ions. Okay, so let's talk about this crystal lattice. So a crystal lattice is defined as an orderly arrangement of positive and negative ions. And so these positively and negatively ions are repeating units. And it's important to note that not all crystal lattices are arranged the same. So a crystal lattice is really a bundle of lots of positively and negatively charged ions bonded together. So let's talk about the factors that affect the structure. So one factors that affect the crystal lattice is the size of the ions. Okay, so for example, if we look at group 1 elements, for example, if I look at the top of the group, there's sodium, and at the bottom of the group we have cesium, and we should know that ionic radii increases down a group. So sodium is a very small ion. It only has the ability to attract 6 chloride ions to that one, whereas cesium is larger, it's further down the group, so it has more energy levels. It's able to attract 8 chloride ions. The other factor that affects the structure is the ratio of cations to anions. So again, remember that sodium and chlorine, if we simplify it, it would be a 1-to-1 ratio. But if I look at a different ionic compound, such as calcium fluoride, calcium is a group 2 element. It has 2 electrons to give away. So if it were trying to bond with chlorine, which only needs 1, then it would have to bond with 2 chlorine ions.
Bonding in a crystal lattice is controlled by the size of the ions involved and the stability of the final structure with respect to positive and negative charge. The attraction among ions occurs in all directions. In sodium chloride, there is 1 sodium ion for every chloride ion. Chloride ions attract as many sodium ions as possible. Similarly, sodium ions attract as many chloride ions as possible. In this way, the charge on each ion is balanced as evenly as possible by the surrounding charges on its neighbors. The ions pack together, producing a regular, infinitely repeatable structure called a crystal lattice.
So a crystal lattice is made up of several unit cells. So a unit cell is defined as the smallest portion of a crystal lattice that shows a three-dimensional pattern of the entire lattice. And the way that they determine this structure is by X-ray diffraction crystallography. So basically they take a sample of the solid, they are bombarding it with X-rays. Those X-rays strike the ions, and then because those ions are charged, they deflect. And this deflection forms a pattern that can be analyzed to determine position.